Hello everyone, this video will show you how to implement the 3-node TH17 network that we just created into COPASI, our modeling software that you just saw an overview. Just to give you guys a reminder, this is our 3-node model. We have our IL6 and TGF beta on the top, and this is our main induction to TH17. When this node is present, this reaction will get activated and we will have ROR gamma T expression. Once we have ROR gamma T, reaction 2 will come in place, IL-17A will be produced. Now let's get just started. Click on COPASI to get started, and we'll create this model from scratch. COPASI will open. Let's put it here in the middle. Okay, perfect. Now, let me tell you, there is an option that is import SBML. So if you click in here, you can select the cell designer file, press OK, and then the model will be created for you, and then you'll just need to create the reactions and the dynamics of the model. Let's do it from scratch though. Let's give a name to this model. It will be TH17 underscore model 3 nodes, for example. We'll press commit. You guys can select any time unit you want. For a TH17 differentiation, we'll select hours and we'll select micromoles. And also for the units, let's select microliters. We can add some nodes in here, and this is the initial time that's set to 0 now. Let's press commit to save. And let's get started. Let's create our first node. So we'll go down to species and we'll double click and we'll give a name to the species. The name of the first node is IL6 plus TGF beta. We can use beta as we can put just a B. The compartment, we haven't created any compartment, but since it's just one compartment, we can either create a compartment in just one or just use compartment as default. Simulation type, we'll select between reactions and fixed. We'll select fixed, and this will have an initial concentration of let's say 1500. We'll press commit. The first species has been created. Let's go ahead and add the second one. The second one will be ROR gamma T. We'll add this name into the species name, one compartment, and these will be reactions. The initial concentration of ROR gamma T will be the basal concentration before it's being upregulated. We can just put 100, for example. And this concentration, rate, and transition will appear later when we run a time course. The third species we need to create is IL-17, and same story here. We'll add IL-17A, we'll use reactions, and we'll define a basal concentration of IL-17A, and we'll press commit. Now that the three species have been created, we have our IL-6 and TGF beta here, that's fixed, and then our ROR gamma T and our IL-17A, that is a reaction type. As I said, these three other columns here will be determined once we run the first time course, so let's not worry too much about it now. And now let's create our reactions. We have two reactions to create. The first one is, we can call it ROR gamma T activation, for example, or if you want to call it expression, but you can give any name you think. The reaction will be IL-6 plus TGF beta transitions in an irreversible manner into ROR gamma T. If we click to commit, the mass action irreversible will appear. Let's make sure though that the names are correct. The value we can give for now it's 0.1, and again we can use any other function. In this case we'll just use mass action. Next, let's create our second reaction. Our second reaction, is IL-17A production. So once ROR gamma T is expressed, IL-17A will be produced. The reaction annotation will be ROR gamma T. transitions into IL-17, as you can see on your screen. Please note that I'm being very careful with the name. If I put IL-17B, for example, instead of IL-17A, and I click on commit, you'll see how now COPASI adds a fourth species named IL-17B. So it's good that COPASI can create for us, but at the same time we need to be careful with the typos. We can just go to species now that ILB has been created, or we can just leave a 0.3 value, for example, and I'll show you how to play with the parameters later. And in species we can just select IL-17B and delete here with this button. Let's click here on delete. Oh, it needs to be well clicked, excuse me. Perfect. All right, we have our two reactions. We have our first node IL-6 TGF-beta that through reaction 1 activates R-arginine, and R-arginine at the same time through reaction 2 upregulates IL-17A. Perfect. Let's take a look now at a third reaction that I haven't mentioned yet, which is IL-17A degradation. If we have a fixed amount of IL-6 and TGF-beta, and by the way, this is how you select a degradation, by just not putting anything on the product side of the reaction. See how there's nothing here? So we can set up the value here. What I was saying is the reason why we want to add degradation is because IL-17A will just build up and the model will never have a steady state if IL-17A is not degraded. That's why we want to add this third reaction, which is degradation. All right, let's take a look at the different tasks that we can run with this very small model. You can see there are a ton of tasks in here. You'll get introduced to the steady state, which is at what point the steady state is reached. There are a lot of parameters here that you can, please feel free to pause the video and raise your hand and we'll help you out understanding what these parameters are. But if you just press run, you'll see how this model reaches a steady state and the concentration of these two are in a steady state at this specific time. Here you can take a look at different compartments, quantities, and reactions. You can check the fluxes of the reactions, but this just gives you an idea on where the steady state or when the steady state is reached in this model. Time course is very self-explanatory. We just need to check how the different concentrations of species will change over time. We can select our duration in hours because that's how we expressed our model in hours. We can change the intervals, and then if we click back and forth between interval size and intervals, you'd see that that changes. So we can either select the size or the number of intervals, and the opposite will be calculated for you. I would just leave this as default, and then let me talk about the output assistant. In COPASI, you don't need to produce your figures, your graphs. The output assistant will do that for you. So if you, for example, click now in output assistant, you'll see how COPASI has a predetermined default plots that can be created for you. In this case, the first one is concentrations, volumes, and global quantity values of the whole model. So if we press create and run, you can see now how a time course is created for us. Now this time course has the species here on top, and you can select and unselect those species, and you can see how this IL-6 and TGF-beta is not represented, and the reason why it's because it's fixed, and as I said, a fixed concentration will always be the same. So this will be a plain line on the 1500 point, so that's why COPASI is not showing this to us, because it's actually not changing. As I said, you can select and unselect, and there are some options here on top. You can click show all or hide all. You can also make a logarithmic x-axis, which doesn't look very good, but for instance the y-axis, if we make it logarithmic, that looks better. We can zoom out. and we can save this data, or we can save the image. So if you want to make this plot with another software, you would save the data, and then that would generate a txt file. Now, something I want to point out is, do you see how, for example, here the ROR is in the level of the thousands, the IL-17 is on the level of the 10,000s. Here I wanted to highlight again the role of the sliders. The slider will allow you to move parameters back and forth. Now, something to note, the time course needs to be selected for the sliders to be active. So do you see how now when time course is selected, the window for the time course sliders is active? Otherwise, we'll give you a message. You can select new sliders, and if we select all the reaction parameters and press OK, click OK, the window will show 3 different parameters here. As you can see, the first parameter is the degradation of IL-17A, the second one is the production of IL-17A, the third one is the expression of ROR gamma T. I want to show you exactly what we are changing. If we go to the functions and we click on the, oh, that's because our slider is on. But anyway, just disregard. Do you see how in the irreversible, let's click OK here. In the irreversible, you have a K1 times substrate. This is the parameter that we will change. The bigger K1, the more product you're going to get. And this is linked to the reactions we set up. So let's take a look at how the plot would change if we change the parameters. If we upregulate the degradation of IL-17, as I'm doing here, do you see how IL-17 is more rapidly downregulated? I can always press here and change the minimum and maximum value. For example, if I want to do 100, I can go ahead, maybe press the logarithmic scale, so the slider will be better manageable. And do you see how now I can modify the quantity of IL-17A? By changing the parameter on the reaction, I'm able to move the curves up and down to my desire. I can tailor those curves for me. Same for the other parameters. See this ROR gamma T? Since it's a state transition, the less production of IL-17, the more ROR. Or if I want to change this ROR with this third slider, the more ROR, you see how ROR will keep going up and IL-17 will go down. Exactly. Let me play a little bit more. See this y-axis here? Let me upregulate this ROR expression, and do you see how now it's a little bit upregulated? We can always change the values and do more drastic changes if you want. Something I want to point out, do you see how this IL-17 is reaching a steady state here, and also how this ROR is reaching a steady state here? This is something that we can change. The reason why these two are reaching a steady state is because the amount of inducer, the amount of IL-6 and TGF-beta is unlimited. Let's go back to the IL-6 and TGF-beta in species. See how this IL-6 and TGF-beta, which is right here on the plot, it's our inducer, our source, is fixed. It's fixed at 1500. Therefore, there are always going to be 1500 particles, or the concentration is always going to be 1500. Now let's change this. Let's put this back to reactions. These 1500 are not unlimited anymore. You can see that by going to the time course, activating the sliders. Let me put this plot up. Now let's change one of the sliders. See how the curves are going down now? And the reason why they are going down is because now the inducer, the TGF-beta and the IL-6 is being consumed. And when there's no more source, there's no more ROR gamma T expression or IL-17 production. Again, these parameters are something that you as a user can change to fit your curves to your experimental data. And this is called manual calibration. You can manually calibrate these parameters, especially when you have these very small models. Alright, so now that we've been over the time course, let me show you, and also the steady state, let me show you a third task you can run. And this is the parameter scan. So what does a scan do? It's very straightforward. It scans, it checks a range of expression of different molecules that you can specify. There are different options of the task, and this is the task that will be run on the background for the scan. Let's select a time course since we're running time courses. And what we will scan first is this first molecule, this first node, the IL-6 plus TGF-beta. And then we will check what happens with ROR gamma T and with IL-17. So here on the reactions, let's check, no, we'll go for the species and we'll check the initial concentration of this node, the IL-6 and TGF-beta. We'll click OK. And now you see how this is something you can change. You can put more intervals if you need more granularity on your plot. And the range we're going to give is from 1 to 1000. We'll leave a time course. And then again, I want to highlight the function of the output assistant. We don't need to create the scan curve. We can just go here, select the first one, which is the scan of the concentrations, volumes, and global quantities of this model. And then we just click create. And let's just run it. As you can see, the task will run. And as the task is running, this plot is being created. You can see how now there are different curves that are being created, and I will get into the results in a minute if you bear with me, but something that I do want to point out is that we have given a very high number of intervals to run this task, and we could pause this task anytime. The maximum is going to go to 10,000, I believe, so if we just click pause, we are able to pause the task, check our results, see where we at. And then if we want to run this task again, we can run it. Let me explain to you how this works. The x-axis is the concentration of our particle that we're scanning. In this case, is IL-6 and TGF-beta. Let's continue scanning that. X-axis, concentration of IL-6 and TGF-beta. And this shows you a concentration of 0 and then an increased concentration every time. And it goes from 0 to our maximum that we determined before running the task. Now, what is the y-axis? The y-axis is the concentration of ROR gamma T, IL-6 and TGF-beta, and IL-17. And this is what you can see in the y-axis. You can see here, let's stop this, it's taking a little bit of time. Again, with a plot you can show and you can hide. Let's show all of them and let's run something with less intervals so you see how it works. This task has been completed now, and see, you can see in the x-axis the concentration. Let's run it a bit more. Yes. So as you can see, we can play with this system. And this is a plot I will talk to you in a minute, but let me first address the scan plot. Alright, let's stop it here. Let's run it. Maybe this is too much. Let's see 300. Alright, this will run. Will take a few seconds. Let's stop it here. Perfect. Let me explain to you this result. This plot, as I said, I'll get to you in a minute. IL-6 and TGF-beta. The more IL-6 and TGF-beta that I'm scanning, of course, is a direct correlation. The more IL-6 I'll get. And this will be an exact correlation. R would be 1 for this one. Now let's check what happens with ROR gamma T. The more IL-6 I have in the scan, the more ROR gamma T I will get over time. Now, do you see how these 100 forms a line, an horizontal line? This is because our initial concentration of ROR gamma T was 100. Therefore, there are always going to be 100 particles, or a concentration of 100 in our scan. But you can see how this is building up. Finally, IL-17. The more IL-6 and TGF-beta, starting at the initial concentration of IL-17, the more IL-17 we're getting. IL-17 is building up. From this plot, you can conclude that IL-6 and TGF-beta in your model is promoting the expression of ROR gamma T and the accumulation of IL-17A, which it looks and very, very simple. It's not very surprising, but in more complicated models, the scans come in very, very handy. Now let me point something out. Here in the x-axis we have concentration. In the y-axis we have concentration as well. So this is a plot that compares an increase in concentration and it checks the concentration of different species. What will happen with time? And now it's when I'm going to this plot that was forming here on the background, was created on the background. Let's run this a little bit with less, even maybe less than that, it will look better. But here on the x-axis we are checking time, we are not checking concentration. The y-axis is being concentration of species again. Let me put it 10 exactly. This looks better. Alright, so let's check first IL-6 and TGF-beta. It's going down. Each curve of this plot means or represents an increased concentration with the interval we give. And maybe we can take a better look if we look at ROR. With no IL-6, ROR is down. As we include more and more IL-6, see how ROR keeps building up and building up and building up? Exactly, it's what exactly I'm pointing out now on the screen. So we have y-axis, expression, and then over time. And we can see how things build up. For example, ROR gamma T. Or for example, other species we can increase the interval, so maybe we can check if there's any correlation on those, or if there's anything that points out to a specific hypothesis that we have. So we can play with this system. So this is the parameter scan. It comes in very useful for in silico experimentation. The next video will allow you to build a bigger model where you can use these tasks.